years present on the dais, and now we are going to hear from a very junior person. But those words will be very profound. He is Devansh Gulati, and he is a first year student from MIT University, and he was an intern at CyberPeace. So we would like to demonstrate the capability of the interns that we intend to develop. Whosoever are doing internship at our CyberPeace, we would like them to develop so that when they go to the market, they are employable and they can really change the world actually. So he is pursuing BTech in degree in cybersecurity, and he has a strong interest in information security, ethical hacking, and network defense. He is currently building a solid foundation in computer systems, programming, and cybersecurity fundamentals with a focus on understanding modern threats and security best practices. Today, he will be delivering a very focused technology focused session on malware reverse engineering. So, once you download the malware, if your system gets infected, then how you will come to know what that malicious code is doing. So, he is going to demonstrate you. And he has taken the malware from malwarebazaar.com and done the research analysis. So, welcome Devansh Gulati, and I hope that you will be able to express and create an interest among these students present here, so that they can also start our internship, very focused internship program at CyberPeace. Thank you. Welcome.
I hope I'm audible.
Yeah, audible.
So, good morning everybody. I'm Devansh Gulati, first year student, currently pursuing my bachelor's in technology from MIT University. I would like to introduce you to the topic of malware analysis. I see a mix of students and respected government officials in the audience, so I invite everyone to take notes as we proceed. Introduction to malware analysis. Let us begin with the most important question. The core objective of this presentation: why do we need malware analysis? Malware, as you know, is a piece of malicious software. When such a code or software is executed on a vulnerable system, it can cause large scale digital damage. This damage may include unauthorized access, loss of money, data breaches, and even disruption of critical services. Malware analysis allows us to study this malicious code in a controlled manner, understand its behavior, and develop effective defenses to prevent future attacks. In short, malware analysis is not a technical necessity. It is a critical component of national and organizational cybersecurity. In this slide, you can see a typical structure of a network packet. The IPv4 packet format, which is highly relevant in malware analysis. At the top, you can see the packet header, 20 bytes long, and organized into 32 bits or 4 byte rows. The header contains critical information such as version and IHL, which stands for Internet Header Length, which defines the IP version, whether it's IPv4 or IPv6, and the header length. The type and total length, which describe how the packet should be handled. The TTL, which stands for time to live, and the protocol used when packets are split during transmission. Source and destination IP addresses indicate where the packet comes from and where it will go moving forward. Below the headers is the most important part of the packet. It is the data or the payload part. This is the part where the actual content of the packet is registered. In malware analysis, this payload is especially important because malicious code or exploits or command and control data often reside here. Types of malware analysis. The slide shows main approaches to analyze malware grouped into 3 broad categories: static analysis, hybrid analysis, and dynamic analysis. Static analysis refers to the analysis of malware without actually executing it on the machine. This is safe and often reveals a lot about the malware. It is subcategorized into 4 groups: signature-based analysis, behavior-based analysis, specification-based and heuristic-based analysis. Signature-based analysis matches the malware against known patterns. These patterns are signatures. I shall cover more on this moving forward. Behavior-based analysis predicts possible behavior by analyzing code structure without the execution of the code. Specification-based analysis checks whether the program violates defined security rules, and heuristic-based analysis uses experience to detect suspicious patterns. Heuristic-based analysis is mostly used in AI systems for analysis of malware based on zero-day vulnerabilities. Dynamic analysis. This type of analysis identifies abnormal behavior during the execution of the malware. This may be encryption of files, tampering with evidence, etc. Taint-based analysis tracks how malicious data moves through the system, and emulation-based analysis runs the malware in an emulated environment to further study its behavior. Hybrid analysis combines both static and dynamic analysis. Static analysis for initial inspection and behavior analysis, and dynamic analysis for behavioral confirmation. This keeps the overall analysis accurate and gets rid of certain assumptions. In practice, there is no single method which is effective. Malware analysis relies on a combination of these techniques to accurately detect and understand the threats. Tools used for malware analysis. There are a plethora of tools to choose from, but these three are some of the most effective. Number one, Ghidra. Ghidra is a powerful open source reverse engineering tool developed by the National Security Agency of America. It was open sourced in 2019 for the benefit of the cybersecurity community. It can be used to disassemble and decompile malicious binaries and has a built-in emulator so as to sandbox the malware inside of it. Binary Ninja is a free and open source tool known for its clean interface and automation support. It focuses on code visualization and also supports scripting and automation which speeds up analysis. IDA or Interactive Dissembler is one of the most trusted tools in malware analysis. It has one of the most effective dissemblers and decompiler support on the field. It is used by professionals and industry experts. Unfortunately, unlike Ghidra or Binary Ninja, it is paid and its license is quite expensive. It is recommended to use Ghidra as it closely rivals IDA and has really upped the bar for open source tooling. Introduction to assembly and register. Assembly is the heart of reverse engineering. It is a programming language that operates at the lowest level possible. We are talking about bare metal over here. Matter of fact, assembly is so close to the metal that it directly gets converted into non-readable machine code from the processor. Unlike high-level languages like C or C++, Python, assembly language is architecture specific. Means it has different versions according to the architecture of the CPU, may it be 64-bit, 32-bit, or of ARM architecture. It can be directly mapped to CPU instructions, and it is designed to give the programmer fine-grained control over the metal. Malware is ultimately executed as machine code, and assembly language is the closest human-readable form of that code. Now, assembly utilizes registers in the CPU to communicate and execute operations within a machine. Think of registers as small storage units. You have your SSDs, USBs, these are storage units, right? Registers are storage units within the CPU that are blazingly fast, and they utilize small values to operate at such high speed. These values are also temporary, so they can be reused over and over again. Let us look at one example of assembly code. Here we see a snippet of the command and control malware, also known as C2 malware. Let us explore this code step by step. So we can see that instead of storing the C2 domain in the .data section, where the string utility can find it, the malware builds on it dynamically on the stack. The first line, push 0x00, it pushes a null terminator on the stack. In C or C++, the strings must end with /0 so that the functions like printf know where to stop. Move, rax, and this hexadecimal address. This is a ciphertext. The malware author that created this malware took the string evil-c2.com. This is the original string. evil-c2.com. This is the command and control domain. And he took this domain and XORed it with the 0xAA beforehand, and now moves that scrambled hex value into a register. Pushrax takes this value and pushes it into the memory, and it's still hidden and unreadable by the code. Now the malware sets up a decryption environment of some sort from here, decrypt loop. Decryption routine. Move RSI RSP indicates that the RSP, which stands for register stack pointer, points to the top of the stack. Since we just pushed our data there, the register source index, also known as RSI, now points to the top of our scramble string. Move RCX11 is the counter. The loop will run exactly 11 times the length of the domain name. If you see over here, evilc2.com is 11 characters long. Move AL 0xAA is the XOR key. XOR is the Swiss Army knife in XOR encryption techniques of malware because running the same operation twice returns the same value. Now, line 15 to 18 is the decryption loop. The XOR byte takes the byte memory address at the RSI, XORs it with 0xAA and stores the result back into the same spot. This turns the scrambled hex into the readable ASCII character. The increment RSI, also known as INC RSI, line 17, moves the pointer to the next byte of the string, and line 18 automatically decrements the RCX and jumps back to the label if RCX is not 0. So that's how the most complex of malwares can be simplified into a bunch of assembly instructions. Reverse assembly is a superpower in the field of reverse engineering. Tag signatures and types. This slide explains how malware is identified and classified into different types of attack signatures. An attack signature is a recognizable pattern or characteristic that helps security systems and analysts detect malicious software. Static signatures. These signatures are derived from static analysis, looking at file headers, hard-coded strings, obfuscated strings, or cryptographic hashes. These signatures are fast and safe to use, but they are mainly effective against known malware samples. Behavioral analysis focuses on the malware when it does run on the system. This may include persistence mechanisms, debugger confusers, command and control servers, file system tampering, etc. Logical signatures. Logical signatures are rule-based pattern matching commonly implemented using Yara rules. These rules are open source, text-based pattern matching definitions used to identify, classify, and detect malware suspicious files or memory strings. These can recognize control flow of the malware, string patterns hidden within the malware, and the overall code flow structures. Static analysis signatures. Header files, which contain the MZ signature, are used in Windows executables. Most Windows executable files begin with the character MZ, which identify the file as a portable executable. These characters appear at the very beginning of the file, and the malware often checks this header before infecting the file. But what if the MZ header was not there? Well, then the malware would be exposed. The malware that are written for Windows executables only search for this header. On the left, we see the C code snippet. The code reads the first 2 bytes of the file, M and Z, buff 0 and buff 1. So, if these conditions are met, the file is treated as a valid executable since it has the MZ header. On the right, we can see the same logic expressed in assembly. So bytes are loaded from the memory over here, and they are compared with M and Z. So 0x4d is actually the ASCII character for M, and 0x5a is the ASCII character for Z. So these are compared with the file, and only then the conditional jump determine whether the malware will execute or it will fail. XOR operators. So this is the XOR operator. It is a bitwise logical operator that is used in programming. This function is efficient and is used by hackers to encode strings such as C2 domains, malicious files, etc. Given below is the diagram for the XOR and its truth table. So you can see over here there's the data and the key, and through the XOR logic gate they are being encoded into A XOR B. So how this works? So the XOR operation takes I'm sure you are all experienced in binary number system. So in binary number system, they are made up of ones and zeros. So if we take a digit, for example, 1 in binary, and we XOR it with 1 itself, it will return the value 0. Similarly, if 1 is XORed with 0 and 0 is XORed by 0, they will both return, if 1 is XORed by 0 and 0 is XORed by 1, it will both return 1. And 0 XORed with itself will return 0. So this is a common technique that is used in obfuscation of code. That's how the code is hidden by the user. This similar technique is used in XOR encryption. So the C logic suggests that a loop iterates over the payload for I is equal to 0, and if it maxes out the length, it will increment till the data is completely XORed. So each byte is XORed with a constant key, and in this case it is 0xAA. After decryption, the payload is successfully executed. This helps hide the payload from static scanners while malware is stored on the disk. On the right hand side, it is the same logic which appears to an analyst during the assembly. So XOR byte decrypts one byte, increment to RSI decrypts to the next byte, and decrement RCX is the decrement counter. The loop is repeated and then transfers execution to the decoded payload jump RSI. So basically, even when encrypted payloads look harmless on the disk, its runtime behavior reveals malicious intent. This is where static analysis fails and behavioral analysis is useful. Yara rules and logic detection. This slide shows how Yara rules are used for logical malware detection by combining different indicators into a single rule. Yara works by defining a set of patterns and a logical condition that determines when a file should be flagged as malware. This matches the pattern inside the file or memory. The Yara rule combines certain indicators into a structured format. You can see over here. This is one rule from the Yara file. The metadata is the human readable information. Over here it is detects XOR root and C2 string, and it is authored by some random name. The string section defines what to look for. Here the XOR root is equated into assembly bytes, and the C2 URL is http://evil.com. The conditional section explains the logic as to how the detection is managed. Here it says that if 2 bytes or 16 bits equal to 2 bytes, which equate to this address 0x5A4D, which stands for MZ in hexadecimal, if it equates and if these conditions are met, if there is a XOR loop present and if there is a C2 URL present, then and only then will it flag the file as a malware. So Yara rules are quite useful for detection of malware as so. Malware defense evasion and persistence. These are some core techniques malware uses to stay hidden and remain active inside the compromised system. Awareness, anti-debug, and core obfuscation. Awareness refers to the malware's ability to understand its environment. It is capable of detecting virtualized environment, sandboxes, security tools, and labs. If the malware thinks that it is being analyzed, it will silently exit, delay its operation, or just disable its malicious intent completely. Anti-debugging is a technique used by exploit scripters to prevent the reverse engineering of their malware. Common methods include detecting debugging environments, using time checks, and triggering crashes when analysis is detected. The third method, code obfuscation, helps to hide the intent of the malware. Encrypted XOR operations, obfuscated code and APIs, and jump and misleading statements are meant to confuse the analyst even further. So this is something that we should watch out for. Environmental awareness is the key defense evasion technique that uses techniques to avoid sandboxes, virtual machines, and analysts. The malware first looks for artifacts that indicate an analysis environment. Over here, we can see that it looks for registry entries such as VMware tools or driver files such as vmmouse.sys. Using these files, it can check whether there is mouse jitter over here and the analysis process like debuggers. So this is a debugger process over here. Malware then checks the hardware profile of the system. These are giveaways for virtual machines, such as virtual machine MAC addresses. If the number of cores are lesser in the virtual machines, typically when we design virtual machines for malware analysis, we tend to keep a lower core count, such as 2 or 3, that's maximum, and a small disk size. Malware also observes how the system behaves, time anomalies using CPU counters, abnormal or closed network ports suggesting an isolated environment, and lack of mouse movement or keyboard activity. Upon detecting such parameters, it will simply execute a dummy script or just simply remain dormant and delete itself. This slide focuses on how malware detects the presence of a debugger and alters its behavior to evade analysis. Debuggers are essential for malware analysis, so detecting them is a common defense evasion strategy. The strategy being used here is artifact detection. The malware looks to certain artifacts left by the debugger. These may include processes or memory artifacts like PEB flags, which stands for Process Environment Blocks. It may also search for breakpoints that are set via the debugger registers, and it often scans its own code and driver linked libraries for this. RDTSC, which stands for Read Time Stamp Counter, is a CPU instruction that returns the number of clock cycles since the system has booted. A clock cycle is the fundamental unit of time in a processor. It is one tick of its internal oscillator, which equates to billions of times per 1 second. So one clock cycle may equate to, for example, 1 billion hertz, 10,000 gigahertz, something like this. So RDTSC is a CPU instruction that returns the number of clock cycles since the system has booted. Malware uses this to detect execution delays caused by debuggers or virtualized environments. The malware calculates the delta cycle, which is given by TSC after versus TSC before. This is basically the time difference between two consecutive clock cycles. Delta over here signifies the difference in CPU clock cycles and is given by this formula, which I just explained. So delta allows malware to distinguish between real execution and instrumented execution. So from this slide, we can see that reverse engineering is not just a skill. It is essential for cybersecurity and the understanding of zero-day vulnerabilities. If we get hit by a malware that contains a zero-day vulnerability, it will be very hard to decrypt it unless we try to reverse engineer it using behavior analysis or static analysis. And reverse engineering is often called the sword of cybersecurity. It is a very important skill to have, and it can improve your understanding further in any field of cybersecurity, may it be threat hunting, malware analysis, or ethical hacking in general. Thank you.
Thank you, Devansh. next speaker is Mr. Arun Mane. He is a cybersecurity professional with 18 years of experience working across automotive, IoT, industrial control systems, security drones, platforms. As the founder and CEO of Aminasec Research Lab, he focuses on hands-on security research, including hardware exploitation, firmware reverse engineering, vehicle security, and industrial automation security, helping organizations understand and reduce real-world risks. So I welcome Arun Mane and his partner to demonstrate the tools how we can hack into the system sector. So welcome Arun Mane and thank you. Participants may ask any question if you feel like actually, so that you can interact actually. Let it be a dialogue actually, not monologue. And we, our friend Mr. Bawa is recording it. He will give you the recordings also, so that you can at the back end when you go home you can review that also. So Mr. Mane, the platform is yours. हाँ निकाल जोशी जी हाँ